Spectroscopic parallax is a means of finding the distances to stars. And this looks like a lot, but all it is just how to use spectroscopic parallax, which is a funny word because it has nothing to do with parallax. But it will let you find distances to stars that are very far away. Here is a spectroscopic parallax problem that the IB may throw at you. So read this, pause it, and see what smart things you can do to solve this problem. Spectroscopic parallax is a pretty powerful method for determining distances because you can take your spectroscope and you can look at just about any star in our galaxy and you can look at its maximum intensity of wavelength. And you can also look at its apparent brightness. And you can calculate some stuff. And this works for far stars up to 10,000 parsecs away. So many of the stars within our galaxy, we can use spectroscopic parallax to figure out how far away it is. And your first step would be to use Blind's law. And you look at its wavelength. And you can then say from that that the temperature of it is going to be the wavelength divided, the constant here divided by whatever the wavelength is. And so you take this 240 nanometers and you plug that in. And you're going to get a temperature that's crazy hot of about 10,000 Kelvin. That's where you start first off. So now that we know the temperature is about 12,000, that's going to be an estimate. That gives us a lot of uncertainty. You then are going to have even more uncertainty because now you're just going to estimate its luminosity from this diagram. So somewhere around in here is 12,000 Kelvin, and its luminosity is going to be something like this. So we know the luminosity of this star is going to be about 10 to the second, or 100 times bigger than the luminosity of the sun. And so that's 10 to the second times the 3.8 times 10 to the 26 watts, which is it's not a bad number to memorize for our sun. And so this star is times 10 to the 28th watts. And so now we've got the luminosity. And now we have a very rough estimate of its luminosity. We know pretty good, hopefully pretty close to the actual value for its apparent brightness. And we can now use this equation for brightness and luminosity and distance to find this magical distance. We rearrange and we're going to get this equation. Once you plug all of your numbers in, luminosity goes into here, this brightness goes into here, you will get something like 8.4 times 10 to the 17th meters. A lot of meters. But we want to know what it is in light years. So you look up the conversion to light years. It's in your data booklet, or it's in that crazy thing called Google, where 1 light year is 9.46 times 10 to the 15th meters. And the answer is about, roughly, with a lot of uncertainty, 89 light years away. And you ask yourself, does that make sense? Would that even still be within our galaxy? And the Milky Way galaxy is something like 100,000 light years across. And so this does make sense. It fits within that.